Thanks, Gustavo, for the kind introduction. Hello, everyone. In today's tutorial, I would like to show you how to characterize defects by using this instrument. And I'm going to show you how you can characterize the defects in your device in both frequency and the time domains. So during my PhD, I worked with perovskite solar cells, and I observed a unique and intriguing feature which correlates to defects observed in the solar cells. And by characterizing defects, we were able to understand this unique feature very well. So today, I would like to show you and show these unique features from perovskite solar cells as an example, and further characterize the defects. So in a solar cell, what you expect is you have to have a absorber material which generates charge carriers upon shining light, and you would be able to extract these charge carriers as fast as possible in order to generate electricity at the end. So perovskite solar cells, the perovskite material itself acts as an absorber material, and it's also known for very good absorption. It generates charge carriers. It absorbs light very well, also generates charge carriers very efficiently. And not only that, the charge carriers in the perovskite absorber are long-lived, means they don't recombine so fast as other materials, leading you to have a better efficiency at the end of the day. So this is the perovskite structure I've shown here, which contains ABX3 structure. You have 3 different elements with different compositions. They're called differently, but typically the high efficiency solar cells contain methyl ammonium, lead, and iodide. And it's known, and this material is known to have point defects, and these point defects are thermally activated defects. And when you have such defects, it will cause certain abnormal behavior in the device, which is what we're going to see today. So when you have fabricated the device with such an absorber along with the transport layers, you have 2 different interfaces between the perovskite and the transport layers. And once you fabricated the device, the first thing you would like to do is to see how well the fabrication went, and you would like to characterize it by using current voltage characteristics. When you measure the current voltage characteristics of these perovskite solar cells, it will appear like this. Of course, it's not an ideal exponential behavior, but you observe increasing current values as a function of voltage. If you look at the voltage response there, when you apply the voltage, you start at some point and you linearly increase your voltage to reach to a certain point. And you do this normally by increasing the voltage in a certain intervals of time. So your current value at the end of the day is not only a function of voltage, but also the measurement time. Ideally, this is called, normally it's called as a sweep rate. Ideally, your IV curves should not depend on the sweep rate or the sweep direction. For example, if I measure from 0 to 1 or 1 to 0, it shouldn't matter. You should be able to see the same result. Let's try to measure the same device a bit fast. So this curve here, IV curve, looks entirely different to what you have seen before. And interestingly, you observe 2 different responses when you measure from 0 to 1, that's a forward, and 1 to 0, meaning you have hysteresis in your device. Let's see what happens if you measure slow. So here you see entirely different response in comparison to what you have seen in the last 2 measurements. You observe a huge amount of hysteresis in your IV curves. And interestingly, in this case, the forward current doesn't show a clear exponential behavior at all. And it contains higher current values compared to the reverse case. In general, hysteresis is quantified by considering the area between the curves. And if you do that, you observe positive values in case of the slow sweeps, and you observe negative values when you take the area between these curves, which is entirely strange, which is not how it's supposed to be. The question is, why do we have hysteresis in the first place? And why do we have 2 different types of hysteresis, and how we can minimize it? It's well debated topic in the perovskite community and mostly accepted. It's well established in the community that the ionic defects in the perovskite solar cells are mobile, and these mobile charges accumulate at your interfaces that leads to hysteresis behavior. Today, I would like to characterize those defects in order to explain this hysteresis phenomena at the end. I'm going to do this in both frequency and time domains. Frequency domain would be impedance measurements, not only impedance usually represented in literature with different representations, permittivity and modulus. I will also, since we are talking about interfaces here, how can I know a defect comes from a bulk or the interface? That also we will discuss. Also, what's the importance of DLTS, what it can tell us in terms of polarity, and also additional information regarding the ionic defects. At the end, I show an approach to characterize hysteresis and the correlation between the defects measured by both methods and the hysteresis. So impedance spectroscopy in general, a pretty straightforward approach. You apply an alternating voltage, and you vary the frequency of your voltage signal. In a linear system or pseudo-linear system, your current response behaves analogous to voltage signal. However, shifts in certain phase. Depending on your current response lags or leads behind the voltage signal, you would observe either a capacitive or inductive type of response. And that's what this instrument does. It measures, it applies voltage, measures the current, and gives you the ratio between them and the phase difference between them. Since we are talking about a time domain, we have a complex quantity containing in-phase component and out-of-the-phase component. And since now we are interested in hysteresis, which is essentially the time, a delay response of current with respect to applied voltage, let's stick to our discussion to the imaginary part. Please keep in mind that when you measure your device, you not only measure what goes on in your material, but also measure the parasitic resistances related to your cables, contacts as well. In such situations, it's essential to do compensation to be able to precisely characterize your device in terms of defects. By assuming certain equivalent circuit model, you would be able to quantify the resistance and capacitance contributions coming from your device. And when you do that, you would be able to mathematically extract the quantities, resistance, and the time constants of your circuit. In principle, a time constant represents what goes a microscopic process that involved in your device. So each peak in the right-hand side picture, which is impedance as function of frequency, should tells you there is something going on at these time scales. And since impedance is proportional to resistance, you observe a mega ohms of roughly about a mega ohms of resistance against to the current flip. But if you want to understand what's the physical process involved in your device, you need a different representation, such as permittivity or the dielectric spectroscopy. In general, if you have a material, there are a number of processes that going on, such as interfacial response or a dipolar or ionic or electronic features. Normally, they're all randomly distributed all over your device. However, when you apply an electric field, all these different processes try to respond and reorient themselves according to the applied electric field. And each of these processes contain their own timescales, and depending on the timescales and by measuring permittivity as function of frequency, you would be able to characterize or understand which process belongs to which type of polarization. Also, on the right side, you see ionic and electronic features. These are the resonance features, and interfacial and dipolar process are normally the relaxation features. So I have shown you here a textbook example of permittivity spectra. Similar to impedance, you also have real and imaginary parts together. And with MFIA, you can measure up to 5 megahertz, which means you will not be able to characterize the resonance features, but you would be able to access the space charge and the dipolar relaxations in some materials as well. Of course, this is not the case for every material you have. You have to cross-check with the literature reported values, but in general, space charge and the dipolar relaxations you would be able to characterize them. So I have shown you on the right side the representation in terms of permittivity as function of frequency. So on the left side, I have shown you how you can obtain the permittivity representation from the impedance spectra, where C0 represents the geometric capacitance of your device. Once you know your thickness and the active area of your device, you would be able to easily obtain the permittivity spectrum. Ideal case, you normally use a Debye model, which allows you to obtain the timescales involved in this relaxation process. So typically, you would observe a certain peak in the imaginary part of the permittivity, similar to impedance. So if you look at the spectra here, you observe a high frequency response. But if you compare to impedance, you observe entirely different. The question is, why is that the case? Am I measuring some artifact, or is it right or wrong? In order to answer this, you need to, it requires a bit theoretical understanding. I do not want to go much into detail, but just to mention roughly, it's because due to accumulation of ionic defects, or in other terms, the long-range conduction of ionic defects that occur at the interface. So in general, the energy as function of distance is shown here. You have ionic defects, they're distributed everywhere in your device, and at high frequencies, you apply a certain alternating voltage. So you would be able to move your defects within a certain limit, back and forth, and you before the defect can migrate from its position, further from its position, you reverse the polarity of your AC signal, which limits your conduction process. This is called short-range conduction, where your defects only migrate within a certain limited regime. But when it comes to lower frequencies, you measure longer times, which allows the ionic defects to migrate very long distances over a series of hops. In that situation, if you have transport layers or electrodes, they would act as blocking layers for ions, because since ions can't pass through, they will pile up at the interfaces, leading to a near DC response at the low frequencies. So if you have such a situation, which is a dominant response in your spectra, you won't be able to characterize the low frequency peak by using permittivity representation. In such situations, there is another representation called modular spectroscopy, which allows you to characterize both peaks in your spectra. So for the first time in the modular spectroscopy, you will be able to see two distinct peaks in both low frequencies and high frequencies as well. So in mathematical terms, modular spectroscopy is nothing but inverse of complex permittivity. By using this relation, you would be able to easily access it. So the question is, we have these two defects, and by plotting them in terms of different representations, you would be able to tell where are they coming from, what is the physical origin of it. For example, in the permittivity spectra, you see a peak. That means you're observing a dielectric relaxation in these frequencies. If you move to low frequencies, you observe a peak that is dominant in terms of impedance, and it doesn't appear in the permittivity spectra. That means this response comes from long-range conduction of ionic defects located in an interface. So these three representations are very useful in terms of not only identifying defects in your impedance spectra, but also to understand the physical meaning behind the process. In addition, these three processes not only allows you to understand the defect origin, but also help you to locate the defects whether they are located in the bulk or the interface. Traditionally, this is done by comparing resistance and capacitance contributions involved in your spectra. If you compare both peaks here, they have 2 orders of magnitude difference, which means their resistivities are different. In the bottom plot, modulus, which is proportional to 1 over C, so in other terms, capacitance, and if you compare the peak heights there, they're almost identical. This can be seen as you're looking at the defect response, the same charge, but moving at different locations where your resistivity would be different. Or, and there comes the question, since ionic defects always form in pairs, it could also be seen as a vacancy interstitial pair moving with a different conductivity. So that's the problem with impedance. It can only detect movement of charge, but it cannot tell you about the polarity. That brings me to the next method, DLTS. Deep level transient spectroscopy, as the speakers talked quite extensively today. It's a time domain approach. In addition to impedance spectra, in contrast to impedance spectra, you have you measure DLTS transient at a fixed frequency. And in addition to AC amplitude, you also have a DC pulse involved. So the method I present right now is slightly, the physical meaning behind the approach for ionic conductor is slightly different in comparison to classical semiconductors. In classical semiconductors, you try to fill your traps with the filling pulse, and you try to understand how the charges will relax back to their equilibrium condition. It gives you an emission rate. But when it comes to ionic conductors, due to the asymmetry in the device, or the built-in potential in the device, these ionic charges will already accumulated at the interfaces. And when you apply a pulse, you will move these charge carriers into the bulk of the perovskite. And when you stop the pulse, they will relax back to the interfaces, leading to a certain transient with a certain time constant. And these time constants are what we are interested in. And the voltage pulses doesn't need to be a voltage, but could also be a light pulse. Also, the transients, you don't necessarily need to look at capacitance, but also you can also measure current or voltage. Each of these methods has their own significance. Some methods, some transients are sensitive to high frequency defects, or another representations are known for slow measurements. Regardless which are the capacitance transients you look at, your transients might contain more than one defect signature in the transient. In such situations, double boxcar method is very useful. So in this approach, you define 2 points, 2 times in your transient, and you try to maintain the ratio between these 2 points constant. You define this rate window properly, and then you move this rate window all over your transient so that you get a collection of time constants. And at some point, these time constants will have maximum, and that's the maximum time constant that you're interested in. And these maximum points, you collect them as function of temperature, and when you plot in an Arrhenius plot, where you have these rates as function of 1 over T, or 1000 by T, you would be able to characterize the activation energy, diffusion coefficient, and based on the capacitance step height, you would be able to characterize the defect density as well. When it comes to the polarity, once you know the background doping density of your material, depending on whether your capacitance step appears above 0 or below 0, in your boxcar approach, you would be able to say the polarity of your defect as well. So in this case, you could say we observe same defects as an impedance. However, these 2 defects are appears to contain opposite charges. However, this approach is not completely applicable when it comes to perovskites, because the background doping density of the material is still under debate. However, most of the community has obtained evidence that it's mostly intrinsically doped material, so you can't really tell much about the polarity of the defect when it comes to perovskite. We also recently found that it's also possible that different defect signature response in DLTS comes due to capacitive to inductive behavior of your defects. By that, what I mean is when you, as we discussed today, based on whether your current response leads or lags behind the voltage, you observe capacitive or inductive response in your signal. A typical, in general, the increasing trends in the impedance spectra as you decrease the frequency is considered as a capacitive response. In the similar way, a decreasing trend in impedance as function of decreasing frequency considered as an inductive response. In this example, exactly the point where you see the transition in the impedance spectroscopy, you observe the transition from one defect type to the other defect type, indicating that this phase transition or phase shift in capacitive to inductive behavior can be also seen as defect with different polarity when it comes to ionic conductors. So far, we have seen both impedance and DLTS are complementary methods. You are able to observe different defects. You're able to locate them in your device, and you can also tell what's going on when it comes to whether a defect comes from with certain polarity. Of course, it's not applicable when it comes to perovskites, but in general, in the classical semiconductors, it works very well. In addition, it also tells us about the capacitive to inductive behavior as well. So far we saw AC condition measurements, AC plus DC condition measurements. Let's have a look at pure DC measurements. So to go back to our initial question, how these defects are related to hysteresis. To answer that, we measured IV curves, current voltage characteristics of the device in an extensive range of sweep rates. As you see, we started with 200 millivolts per second, and we measured up to 2000 volts per second, different sweep rates. And we applied a voltage pulse completely under DC conditions, triangular voltage, both forward and reverse directions, and we observed two entirely different responses. So just to make sure, these measurements were done back then by using an oscilloscope, but in principle, you can also measure the same measurements by using MFIA. To make the comparison between impedance and hysteresis in IV curves easier, we converted the voltage axis to a frequency axis by dividing the voltage with a scan rate. So that's not physically feasible. It has no meaning, but it gives you an idea what goes on at what frequencies. So as you see, clearly there are two defects. In the middle, you hardly see any hysteresis, but in the low frequencies and high frequencies, there is hysteresis. At low frequencies, it's quite significant. It also changes the shape of your IV curve, also contains negative resistance, negative differential resistance, indicating that it's an inductive response. Let's measure area between these curves. So this is the hysteresis area on the left side and as function of frequency. In similar to impedance and DLTS, you also observe two different defects, two different defect peaks. In one case, it's prominent, in another case, it's not. So how these defects are related to impedance? Let's plot impedance as well. So on the top curve, I plotted modular spectroscopy. On the left side, I've shown you the phase difference between them. As you see, they're exactly at the same spot where you expect defects in impedance, indicating that these defects that we measured by using DLTS and impedance are the responsible ones for hysteresis observed in IV curves. And these defects are located bulk in the interfaces, and they lead to capacitive and inductive response, which is the cause for different types of hysteresis here. And they likely contain the same polarity because it appears the hysteresis originates due to different conduction types rather than two different defects here. So to answer why this instrument, so as you see, you can use MFIA quite nicely to understand what's going on in your device. And it's very useful in terms of impedance measurements because, as you saw, there was a low frequency defect, which appears at very, where you have to measure slow. In that situations, the one period averaging offered by the device makes your measurements faster. As you saw, we require voltage and current light pulses in order to excite your device. In terms of DLTS, you can use MFIA to generate voltage pulses. Also, you can control light by using PLL loops. Also, as Ron today showed us, you can measure the transients quite fast. You also have continuous streaming. There is no recovery time. And the DAC module allows you to have a precise triggering and averaging as well. As discussed, you can also do DC measurements by using the scope module. With that, I hope today's talk gave you an overview about what type of defect methods that you can use and how to characterize your device and how to identify defects in terms of bulk and interfacial response. And I'm happy to answer any questions you may have.